Okay, well, let's look at what we've done here. So in this example, we are looking at our more complex gear mechanism where we have a 20 tooth to a 12, a 20 driver, a 12 driven, a 20 driver, and a 12 driven. And by the end, we have a really fast spinning axle when you take all these gears and put them together. So what we have is first a 20 to a 12, and then connected to that same axle of the 12 tooth is a 20 to a 12. So we have a ratio of our teeth of a 20 to a 12, which is reduced to be a fraction of, or a ratio of 5 to 3. Well, if we multiply those together, so 5 to 3 times 5 to 3, well, we have a 3 times 3 is 9, and a 5 times 5, which is 25. So the number of rotations for the driver is now 9. This 20 tooth is a driver, and this 20 tooth is a driver because it's connected to an output, which is the driven. So our rotations for our driver is 9, and the rotations for our driven is 25 because 5 times 5 is 25. So when we express this as a gear ratio, like we had our 3 to 5 in the mechanism that was a 20 tooth to a 12, for every 3 rotations we get 5, we know that that's almost a 1 to 2. It's almost twice as fast using this mechanism. This smaller gear is spinning almost twice as fast as the larger gear. But when we use this new gear multiplier, when we use our gear system so that we have 2 outputs, we have 9 for our output. For every 9 revolutions of our main output, we end up with 25 at the end. This last one is spinning 25 times for every 9 times that spins. Now that's a really weird number to work with, so we use it for something approximately close to it. So if it were actually 27 times and not 25, a little bit more, we would see that, oh, it's 3 times as fast. For every 1 time this spins, our output, the driven, spins 3 times. So by adding this, we've increased it from about a 1 to 2 to be almost a 1 to 3, which is seen, evidenced by the speed that it crossed the finish line. So hope you enjoyed this. Good luck in your designs and happy racing. We'll see you soon.